And we're going to move on to the next talk by Ramon Fernández Mir, who's going to talk about convex optimization in Lean.
Yes, hello.
You share your screen?
Yes, yes. Can you see it?
Yes.
Yeah.
It works. Okay. So.
All right. Hello.
Yeah.
Yeah, I'm very excited to talk about CVX Lean today. So this is a project that was started originally by Alex Bentham and Jeremy Avigat about 4 years ago or so. So today I'm going to give you an overview of the project because I think most people won't be familiar with it. And then I'll show you some of the new features that I've been working on in the last year or so. So let's start with some motivation. So why do we care about convex optimization? So well, it turns out that many problems in engineering, such as analyzing the safety and stability of systems, in power control, communications, electronic circuit design, and also problems in finance, such as portfolio optimization, and so on. It turns out that many of these problems can be solved using convex optimization tools. So these are a generalization of something that people perhaps are more familiar with, linear programming. And it allows us to express a richer class of problems, but with a nice benefit that they can be still solved efficiently using this class of algorithms, these interior point methods. One issue with this approach is that there is a large gap between the problem you start with and the problem that you end up solving. And our hypothesis is that Lean can help to bridge this gap. So how do problem of convex optimization problems look like? So they look as follows. This is the standard form. We're optimizing over X, and the F's are convex. I put a reminder of what convex means. So if we can trace a line and we stay above the function, a straight line, and we stay above the function, we're convex. And for sets, if the straight lines stay within the set. So this standard form, this inequality form, is how you would normally write your problem. And an important remark here is that your F's can be, well, your functions in general can be arbitrarily complex expressions, depending on the problem you have at hand. But that's not what solvers want. So solvers take as input a low-level format as this conic form where the objective is linear. You have one affine constraint, and then the rest are cone membership constraints. And a convex cone is just a convex set that is a cone. So it's closed under multiplication by a positive scalar. And there are some examples here. We don't need to go into the details, but like the quadratic cone, the exponential cone, and so on. And you have a limited set of cones that you can play with, and you can tell that the solver can understand and solve for. So how do we go from standard form to conic form? The common approach that is used in practice is this thing called discipline convex programming. And the idea is that you tag a bunch of functions that you understand well. So this would be, I don't know, the exponential or square root, powers, addition. And you tag them with their curvature and the monotonicity of their arguments. And the framework has rules on how combining these functions yields convex or concave or affine expressions, because it is not straightforward to check that an expression, if I give you an arbitrary mathematical expression, whether it's convex or whether this inequality gives you a convex set. So if we have a problem made from these functions that follows the rules, we'll say that it's in DCP form. And then for every function, we associate this thing called the graph implementation, which is essentially a mini optimization problem that represents it. So for instance, if I find e to the x can be represented by minimizing this t subject to this constraint in the exponential cone. So the key idea here will be that every time I find e to the x in my standard form convex optimization problem, I'm going to introduce a new variable t. And I'm going to replace it, and I'm going to add a new constraint in the exponential cone. So the workflow, if you are a user that that is using one of these convex optimization tools. You start with your original problem, and perhaps this original problem is not it doesn't follow the rules of DCP, so you have to do a little bit of work there. And this is usually done by hand. And with these users have some degree of expertise on how DCP problems should look like, so they will often design the problems with this in mind. Once it's in DCP form, there are frameworks that can automatically reduce it to conic form. And there are many frameworks that I list here. The most popular one is perhaps CvxPy. And once the problem is in conic form, I can send it to a solver. Again, there are many low-level conic solvers, such as Mosaic and Laravel Ecos. Mosaic is the one that we'll use in this work. So what are some issues? Of course, if you are doing these pre-DCP transformations, these transformations that put the problem in DCP form, if you're doing them by hand, you have little to no guarantees that you are preserving equivalence between problems. Essentially, we want all the problems along that pipeline that I showed to be equivalent. And DCP transformations are a little bit better, but they are syntactic transformations, and sometimes they are a bit subtle and require proving some side conditions. And in unverified frameworks, this is not done in a very principled way, and they rely on some properties that we know about atoms and about from convex analysis that are assumed about these atoms, but they are never verified. So in Lean, we have the opportunity to actually verify all of these properties that DCP relies on. So this is the solution that we propose. We propose CvxLean, which is a framework, just very much like CvxPy or the other frameworks that supports verified and interactive pre-DCP and DCP transformations. And the interactive part is also important because it allows users to really explore how they can change the problem, yielding equivalent problems, but in a verified way. So what are the building blocks of CvxLean? So the type of optimization problem, so in particular minimization, is pretty straightforward. I just need an objective function from some domain to some range, which is usually the real numbers, and some constraints. And for instance, the type of solutions, if you give me a point that satisfies the constraints of the problem, and such that for any other point, the objective function is bound by it, then we say that that's a solution. So the definitions are pretty straightforward. So how do we define a problem? We have some nice syntax to do that. So this is how problems look like in CvxLean. So I can simply say, I want to define an optimization problem over X and Y, minimize these objective functions. So here I have an objective function involving the square root, and I can have some constraints, as there's a nonlinear constraint there as well, and so on. And this is a term of type minimization from R plus R to R, as expected. So how do we do it in CvxLean? How do we reduce this problem to conic form? So the idea is the same. We check the DCP rules and replace atom applications with their graph implementations. So in the example I showed, there is a square root of X minus Y. This needs to be replaced by this constraint in the quadratic cone, introducing a new variable. It's not important in the definition, but the point is that this is the same as saying t squared less than X minus Y. But on top of, so this is something that unverified frameworks will do as well. But on top of that, every atom needs to include proofs that by doing this replacement, we are preserving equivalence. So when we declare an atom, for instance, square root, we have to provide its signature. So we say it's concave. This means that it's increasing in its argument, and we provide its graph implementation. So this is what I said in the previous slide. So introduce a new variable and introduce this new constraint, basically. And then we have 4 proof obligations that are automatically generated depending on the signature of the atom that we are registering. And I'm not, I won't go into a lot of detail, but basically they ensure that the atom is equal to that mini optimization problem that we've shown, and then we'll be able to combine all of these proofs as we unfold all of the atoms to prove that the two problems are equivalent. But I wanted to point out the condition because, as I said, in the issues, other frameworks won't check side conditions very well. Here, we actually, if we want to unfold the square root atom, we need to prove, we need to convince Lean that we satisfy the condition. So that is a place where we are immediately better than other frameworks, because if you model a problem in another framework and it turns out that you are not in the correct domain, so you don't satisfy the condition, you will eventually solve it and you'll get infeasible. But here, I'll show this in the demo, you'll actually get, hey, this condition was not satisfied, there's something missing in your problem, or it's over constrained or so on. So let me give you an example. So this is the running example that we were talking about. So this is the example in standard form, or almost in standard form. And this is how its reduced version looks like. So we've introduced a couple of variables and some constraints, and there is a direct correspondence between each component of the original problem and the reduced problem. So the square root reduces to, I introduce a new variable and I add this constraint. This equality constraint is pretty straightforward. It just reduces to this constraint in the zero cone. And this nonlinear constraint, in this case, it translates to two constraints. This is basically an inequality constraint, and this is again a constraint in the quadratic cone. And of course, all of this is needed in order to be able to solve the problem. So we have this solve command that first applies the DCP transformation and then calls Mosaic, and it gives you a solution and it puts it in the Lean environment so you can check what solution you got. So now I want to talk, so this so far is an overview of what CVX Lean has been able to do for a while. And I want to talk about some new features and also shows a little bit more complexity on what can be done in CVX Lean. So I'll show you a bit of a more complex atom. So there's the Huber loss function, which has some applications in statistics. And it turns out it can be defined as an atom, but it's something that is a bit different from what we showed before with the square root, is that in this definition, the objective is not linear. So we have a power here. This constraint has an absolute value. So these are indeed other atoms, right? And usually in other frameworks, this just means, okay, you need to reduce again until you can put it in conic form. But for us, it's a little bit trickier because every atom also has proofs. So in order to make this work and so that you can define this function in this nice way, we needed to do some proof engineering to combine the proofs of the reductions so that the generated properties would hold. So this was a little bit of work, but now it works, and we can have these more complex functions defined in CVX Lean. And another new feature that I'm very excited about is it has to do not with the DCP step, but with the pre-DCP step. So if I give you the following optimization problem, again, pretty simple. So just a couple of constraints, one constraint on x and 1 divided by square root of x less than e to the x. You try to solve this, and any DCP framework will say, hey, that's not DCP, I cannot verify that this is convex because I expect inequalities to be convex less than concave, and you're giving me something that in the right-hand side is convex. So that's not good. But it turns out that it's in this case, it's kind of easy to see that if I rewrite this term like this, then everything's fine. So here I have the exponential, a convex function, a concave function. So life is good. So of course, in a Lean environment, the users can can rewrite this problem and turn it into that form. But the question that we asked is, can we automate this in some way, right? And we came up with the following solution. So we're using e-graphs or equality graphs, which are a way to compactly represent a set of equivalent terms with respect to some given rewrite rules. And the idea is that you can keep applying rules in a non-destructive way and increasing your e-graph. And this will represent all the terms that are equivalent. And it's a bit of a brute force approach, but in a smart way. And it's particularly useful when your rewriting task is not really a simplification step. So, for instance, what we showed, there's no clear normal form. There's no clear notion of I am more DCP than this other term. So in this particular types of problems, that's when something like an eGraph-based rewrite system is useful. And we use Egg, which has become quite popular recently. It's an eGraph library written in Rust that it's very efficient and it's highly customizable. And we need to provide it a few things. So we give it a language to encode optimization problems. We give it some rewrite rules. Here we have 67 that were useful for our examples, but the point as well is that I can just give it more and it's not a problem. I need to tell, a lot of our rewrites are conditional, so I need to instruct Egg how to deal with those. And of course, I need to tell Egg how to detect that some terms are in DCP form. So let me show you an example of an eGraph. So this is the first constraint in the optimization problem that I showed before. And you have nodes, and every yellow blob is an equivalence class. And it starts like this. So there's a node per equivalence class. And as I apply rewrites, I will add more nodes and I will merge equivalence classes. So this is after rewriting the inequality. This is after rewriting commutativity. This is a clear example here because of this mol equivalence class. We added a new node and that have arrows pointing in opposite ways with respect to this one. And we can keep applying and so on until we get a huge eGraph representing many equivalent terms. So in our case, we have an eGraph that represents a set of equivalent optimization problems because we have set up the rewrite in a way that they preserve equivalence. And once you've built this eGraph, or you can tell it, you can instruct Egg how to extract the term that minimizes some cost. And in our case, yeah, the cost is the curvature. So we want to extract a term that follows DCP rules. And if you can find that term, then you can ask for an explanation of why that's equivalent. And that's basically a sequence of rewrites that take you from one term to the other, right? So Egg gives us a sequence of rewrites that take us from the original problem to the problem in DCP form. And then what we do is we replay the proof in Lean. So this idea started by Andres and Sid. I think Andres is somewhere here. But hey. Where they built this interface between Egg and Lean, and I reused it and specialized it for this particular problem of rewriting optimization problems. And yeah, what the idea is that every rewrite that Egg gives me corresponds to a lemma in MATLAB. So for instance, the first one I showed here is a simple application of if. Again, a bit of sort of tricky part about this is that it's a conditional rewrite, and in Egg we use interval arithmetic to keep track of the domain of the variables and every expression. So for instance, because we know that x is bigger than 0, we know that square root of x is bigger than 0. In Lean, we don't really have any tactic that can handle all of these positivity goals. So we do our best with the current existing tactics. I saw biapprox recently, so maybe that could be useful to to replay that by approx with a combination of interval arithmetic could perhaps be useful. But yeah, here's a little challenge to the community that it'd be great to have better nonlinear arithmetic. And yeah, now let me give you a little demo. Let me show you how this looks like. I think I might need to reshare. Can you see my VS Code?
Yes.
Yeah. All right. So yeah, first I wanted to show the two examples that I showed in the slides and just convince you that they work. It's a bit unfortunate to have a non-computable section here after the discussion that we had earlier, but but I really thought that this was the same as putting non-computable everywhere, like before every definition. But anyway, so this is basically the same example that I showed for the DCP section of my slides. And yeah, we can solve it. We can look at that it's primal and dual feasible. That means that it's optimal as well. And we have the solution and the value. These are floats, so that's a bit of, so everything is verified up to the point where we send it to the solver, and when we get it back, what we get is a floating point number. So there's a little bit of a mismatch there in types, but still it's useful to have these in your environment, and then you can do whatever you want with them. For an interesting remark that I was saying, if we remove this constraint, then CvxLean will complain and will say, hey, I could not unfold square root because I could not infer that its argument is non-negative. So that's a nice little error message that we can get there if we are not careful in the way we design our problems. Then the second example from my slides. So again, if I try to solve it, yeah, CvxLean complains because it says, hey, I expected this atom to be concave, but atom is convex because this right-hand side is convex. But we can apply all of that E-graph machinery to fix this. And to do that, so every time I want to change a problem, I can enter this equivalence mode. And what this is saying is, I'm going to give you some tactics here to build an equivalence between P2, which is an existing problem, and Q2, which is a problem that will be added to the environment. And this is the witness of the equivalence, right? So I enter this this tactic mode. I apply the pre-DCP tactic. Here we get a slightly different term, but it's irrelevant because it still follows the rules of DCP. And we can solve it again, and we can see this just shows the reduced version after solving it. So in conic form, I can look at the status, solution, value, and so on. And then I also wanted to show a slightly more complicated example coming from geometric programming. So here, this is an example from CVxPy, where the idea is that you want to maximize the volume of a box. So you have these optimization variables, height, width, depth, and you have some constraints on the area of the wall, of the total area of the walls, the area of the floor, and some constraints on the ratios between height and width, and depth and width. And this problem is not convex because we have here multiplications of, we have these non-linearities, which we cannot solve directly. But a common trick is to do a change of variables. So we also have tactics like that support these common transformations of optimization problems. So I start with a problem in this form, and I can apply change of variables, and it will simply replace everything by its exponential. And then I can do pre-DCP and put it in the right form, because here we still had some problems. So DCP would complain about this. It won't be able to know that this is convex. It will say convex divided by convex. I don't know. So we need to do a little bit more work, but pre-DCP can handle that for us. And then we can solve it. And again, we can just see what the solution looks like. And this is the equivalence witness I was talking about. So we can see that the original problem is equivalent to this problem after the change of variables and changing the constraints slightly to make it possible to reduce and solve. Yeah, so yeah, that's almost everything. So I wanted to throw in some resources about CVX Lean. So Alex and Jeremy wrote this preliminary paper on the ideas about the project, verified optimization. You can also read about in particular, more about the maths on how the DCP step is verified in this paper, verified reductions for optimization. And of course, you can see the code in this GitHub repo. And yeah, the conclusion. So I've shown these two steps, and here I've added this little equivalence sign to show that yeah, we provide equivalence witnesses for those two steps, and but also it's not only the verification; it's also the nice interactive environment to change and explore your problems. And the next steps are all related to making the tool. So we really want to engineers and people who use other convex optimization frameworks to use this tool. But of course, the challenge is always that we cannot expect them to learn Lean necessarily. So we want to hide a lot of that complexity away. And sort of the idea is to have these high-level tactics there. So if they know how to use the solve command and the change of variables and like a few others, they don't need to learn every single. They can just be restricted to a nicer set of restricted tactics to change their optimization problems. Of course, more advanced users can even build their own custom tactics if they want. Then, of course, documentation, tutorials. We've seen some great tools to the documentation, so that's something that I really want to do for CVX Lean. And yeah, formalize more examples. So there's like a long list of examples online, such as the ones here. And that's something, if anyone wants to play around with CVX Lean and contribute, that's an easy way to contribute. Just pick an example that you like, formalize it, and make a PR. And I'd be more than happy to discuss that. And yeah, that's everything from me, I think. And I'll take questions now.
Okay, thanks a lot, Ramon. Very nice talk. We have a few questions. First one by Martin.
Sure.
Hello. There was, it looked like a keyword equivalence.
Yeah.
Does it actually change the definition of the Q3 that was written next to it, or?
So Q3, maybe I'll share again. Q3 didn't exist before definition was. Q3 is a new name that. So
Q3 didn't exist.
Q3 exists, but Q3 doesn't. So like when the equivalence command is over, it adds Q3 to the environment. So.
But and the keyword solve Q3 change, is it like side effectful or?
Solve Q3 doesn't change Q3, but it adds some things to the environment. So it will add these reduced. Maybe this dot notation is a bit confusing. It doesn't change Q3. It just adds new constants to the environment. So these are just new things, but Q3 stays the same.
So it like adds a new on side of Lean is like adding a new type on top of it, such that it has those functions like status, or what is it on the Lean side?
No, this dot that's just like that's the name of the definition. It's not like we're adding more fields to the minimization structure or anything like that. So maybe that's a bit unfortunate. It could be called this maybe. So yeah, Q3 is added to the environment here and then modified by solve. And then, sorry, not modified by solve, but solve does add some things to the environment. That's what's happening.
Thank you.
Yes.
Okay, we have another question by Thomas.
Yes, thank you. When you do the egg rewrite, do you have a limit on the number of rewrites, or are you guaranteed that it terminates?
I have limits on the number of nodes that so I first try with, I don't know, 5,000 nodes, and if I can't, I just go a little bit further. So that's one way. I've also experimented with stopping as soon as you find the first DCP term. That also works quite well. It's still a little bit work in progress, I guess, but the best solution is actually to put limits on number of nodes and just increase them iteratively until you find something good. Because yeah, otherwise it can just explode. It can just explode.
Right.
But yeah.
Okay, thank you.
Okay, we have one last question by Mario.
Yeah, so the when you improve the equivalence of two optimization problems, that means that they have the same solution, but they don't necessarily have the same domain, right?
So that means that you have an equivalence is maps, forward maps from the domains of the forward and backward maps from the domains of the optimization problems, such that they map feasible points to visible points and optimal points to optimal points.
So then that means that when you get this Q3 value, this is actually like the wrong, or maybe
this
solution.
This is the wrong solution to this. Yes, that's a very good.
It's not a solution to P3.
It's not a solution to P3. No, that's.
So you would have to apply some additional, like,
yes.
can you take that solution and then like apply some auto-generated function or like functions that are generated as a result of all this proving in order to get.
That's a great question, right? And so I really want to do that, and I want to chain equivalences. So essentially what you want to use is this, right? This is you have this function that would take you back, would take the solution point back to the point in the original domain. But I'm having trouble computing with this function. So I need, first of all, yeah, this is in reals, and this can be a quite complicated function to build this map. So I can't apply it directly to the solution point and compute something, right? So I was trying to get this working for the demo, but it turned out to be a little bit tricky to reduce it to a floating point function. So what we usually do is we, at the level of expressions, every time we see, like, I don't know, real.x, we replace it by float.x. But this function, it turns out, is more complicated because it has all of the proofs and so on. And I was struggling to reduce it to the right map. But you're absolutely right. I was cheating here, and this is not the solution to P3. This is just the solution to Q3. Yeah.
Okay, thanks.
Okay, I think we're a little bit out of time now, so maybe extra questions can be asked on Zulip or at the coffee break. So let's thank Ramon and Maria again